Okay, so far I think we have started discussing about sampling theorem. So the means why we started discussing this is because we have already done the amplitude modulation and the frequency and phase modulation. So this is something we have already seen, that how that works and what are the relative benefits or what are the pros and cons of these things. And then after that we have promised to start another form of analog modulation, which is probably the boundary towards digital modulation. So this is called the pulse modulation. So there are few types of pulse modulation that we have talked about. One is called pulse amplitude modulation, where the information actually is being carried over a pulse, but it is on the amplitude of the pulse. So basically if you see, instead of using carrier in pulse modulation, instead of using carrier like analog or means all other analog version like amplitude or frequency modulation, what we are trying to do is we have a pulse train which looks like this. Okay. So we have a pulse train. It might have different shapes, so that is something we will explore. We have this periodic pulse train, and then we want to modulate our information on this pulse. So pulse is almost working like a carrier. So what we can do is, there are three types of pulse modulation. We have already discussed that. One is pulse amplitude modulation. So in pulse amplitude modulation, what we do, suppose we have a message signal. Okay. So depending on and suppose this is the pulse train which goes like this. Okay. It will have uniform period of either T or Ts, let us say. So basically what we do, we modulate the amplitude of the pulses according to the input signal. So it will be, let us say this becomes the envelope of the pulses, and the pulses are just sitting like this. So basically the amplitude of the pulse or the relative amplitude of the successive pulse actually carry out the message information. So this is one kind of pulse modulation. This is called pulse amplitude modulation or PAM. So that is something we have seen. We have also talked about very briefly other two version of pulse modulation. One is called the pulse width modulation. So like in the carrier we had amplitude, we had frequency and phase. For pulse also there are few things which actually can tell us about modulation or possibility of modulation. So one is of course the pulse amplitude, that can be varied. Also the pulse position can be varied according to the amplitude of the message signal. So what we can do, this because it is a periodic one, so it has a definite pulse position. Now we can start varying this position of the pulse, keeping the pulse width and amplitude same according to the message signal. So let us say we can have this convention that whenever the pulse amplitude is higher, then probably we will deviate from the center point little bit more, whereas whenever the amplitude is lesser, we will deviate much lesser, and something like this. So with this we can have a pulse position modulation where the pulse width remains the same, pulse amplitude remains the same. It is the pulse position relative to where the pulse should be, original pulse should be, original periodic pulse should be. So if we do that, then the position of the pulse is actually carrying the information of the about the message signal. So that is one way of doing it. Another way of doing it is, now because we have three parameters, one is the pulse amplitude, other one is the pulse position, and the third one is the pulse width. So we can also do pulse width modulation. Okay. So this one was called as pulse position modulation, and in width the pulse remains in the same location as the input. Sorry, it should go from here, okay, as the input, but the width will be now varying according to the amplitude. So this might have a higher width, next might have a lower width and so on. This might have a little bit higher and so on. So, basically the pulse amplitude remains the same and the position remains the same, that is starting point of each of the pulse, that is fixed at after every Ts duration the next pulse will be starting, but the width of the pulse will be now varying according to the message signal. So, these are the three possible modulation that can happen. So, we actually call these kind of modulation as discrete time modulation. So, basically earlier whatever we were doing, the signal was continuous time because we had a carrier and that was existing for all the time instance, whereas pulse that exists for some duration of time, rest of the time there is nothing. So, we can call this as discrete time modulation, whereas the amp means the information that it carries, that can be that is not discrete, that can take any value. So, either it is in width or position or amplitude, that can take any value. So, that is why it is still an analog modulation, because the information that it carries, that is in analog form, that is not discretized. Okay. So, to develop the theory of this pulse modulation, what we have started is something like this. Initially we have talked about a theorem which is well known and all of you might be already knowing in some version. So, we have given a theorem which is called the Nyquist sampling theorem. Okay. And at that point what we have taken, so I am just quickly recapitulating what we have done. So, Nyquist sampling theorem means the pulses were, we still had pulse train, but the pulses were impulse. Okay. So, individual pulse was just an impulse function or we should say Kronecker delta function. Okay. So, it is just a delta function, continuous time delta function, so which is defined as the pulses. Okay. With that we started actually started doing almost like pulse amplitude modulation, or we were rather telling that because it is an impulse function. So, we were actually telling them as if we were taking samples of the signal. So, if we had a signal, we are just multiplying by this. So, what, because if we multiply by delta, it will just pick the sample at that instance. So, it was just picking this instances, the sample value at that instances, and these sample values were now were represented as discrete time continuous amplitude. So, it is still analog signal. Okay. So, what we could see from Nyquist sampling, that basically the spectrum, suppose this particular signal, just the signal has a spectrum like this, it is a band limited signal from -b to +b. If we just sample it, it goes down by, so suppose this is 0, goes down by actually 1 by Ts, where Ts is this, or 1 by Ts is the frequency of those pulses. So, basically it goes down by 1 by Ts and it gets repeated at the sampling frequency. So, basically if this is 1 by Ts, so this will be 1 by Ts, next will be 2 by Ts and so on, and similarly it also gets repeated over here -1 by Ts, or you can call that as Fs. Okay. So, this is what happens, and then whenever you do sample, why we are sampling it, we want to reconstruct the signal. So, that was our target, that if we sample it, we should have provision to extract the signal. It is almost similar like modulation, that we modulate, we must have a, means whenever we do modulation, we also have some mechanism to actually demodulate it, so that we get the original message signal back. Here also we are trying to do same thing. We are trying to see if we sample it, or let us say with impulse train we are doing pulse amplitude modulation, then we need to have a mechanism which takes my signal out undistorted. So, if that has to happen, then as you can see, this spectrum of this signal is remaining intact as long as we have already proven that this Fs, see this is B, this is B, that Fs is greater than 2B, or I should say greater than equal to that, equal to becomes that Nyquist sampling rate. Okay. So, as long as that is happening, there is no problem. If it is not true that Fs is less than 2b, then what will happen? Whenever I do this sampling, so that means actually you are undersampling. So, you take a sample over here, because Fs is less than 2b. So, what you do, you take a sample over here. So, this will be the second sample, probably this will be third sample. So, if you undersample it, then what will happen? This things, so because Fs is now no longer, so this is Fs no longer greater than 2b. So, there will be a interpenetration of these two spectrum, and then what we have a distortion over here. Okay. So, this is called aliasing. Okay. So, the spectrum will look like, because these two will superimpose. So, it will be smoothened out over here. So, it will look like something like this. Okay. So, if you now see, this is not equivalent to our message signal. So, if I satisfy the Nyquist criteria, that means my sampling frequency is greater than twice of the bandwidth of the message signal, then I can always say that I can employ an ideal low pass filter, okay, which will exactly take out, because there is no aliasing, there is no superimposition of the neighboring that spectrum that is being created, side spectrum. So, there is no overlapping. So, the spectrum remains intact, and I can put an ideal low pass filter of bandwidth b, and I can extract my signal out. So, if this Nyquist criteria is satisfied, I can get the signal out. That is the whole thing. In a way, you can also explain this physically. So, if suppose I have a signal, what we mean by highest bandwidth? Okay. So, highest bandwidth, suppose b we are saying, that means that is the highest frequency. So, over a unit time, because this is the highest frequency, so there will be restriction of rate of change of this signal. So, basically if my sampling rate is somewhere related to this particular bandwidth, so basically I will ensure that I sample at an instance where I can still have the tracking of the signal. So, what does that means? That actually means, suppose I have a signal like this, and because these variations are there, so a particular highest frequency component is already there. If I start sampling it like this, then what is happening? If I try to reconstruct it, this sample and this sample, the easier method is interpolation, and if I interpolate them, you will see probably it will be smoothened out. So, all these variations are not getting captured, whereas Nyquist criteria is saying that I have to, depending on the bandwidth, I have to take enough number of samples, so that this particular variation within time is being captured by those samples, and Nyquist criteria actually tells what are the minimum number of samples depending on the bandwidth of the original message signal are required to represent this signal. Okay, so, this is something we have already done. We have proven the Nyquist theorem also, and we have done another part of it, which is called the interpolation theorem. So, basically what we have shown through interpolation theorem. So, I am just recapitulating all these things. We are not again mathematically proving it, because that part we have done. So, what we have said, suppose I now have just the samples. Okay. Whenever we say we pass it through a low pass filter, so low pass filter, if you see the transfer function, that is basically a box function. So, what will be the corresponding Fourier inverse transform? That should be a sinc function. So, if this impulses are passing through this particular impulse response, so there should be a convolution, and everywhere a sinc function will sit together, sit one on top of one another, and we have also proven that the zeros are exactly over the other samples. So, if you start putting all those sinc function, and we have proven that if you just at every sample you start putting the sinc function, corresponding sinc function with this amplitude. So, you will see the whole signal, those sinc function getting added will create the original signal, original message signal, which will just go through those steps. Okay. So, this is the reconstruction theorem. So, we have already told that a GT message signal can be represented as this G of k T s. So, these are those sample values multiplied by sinc function. Okay. Sinc function appropriately delayed. So, depending on the value of k. So, that is why you are putting a sinc function over here, depending on the value of k. If k is 0, you put a sinc function over here, k is 1, you put a sinc function over, and so on. Okay. So, accordingly you fill up all the sinc function, and that should give you the original message signal back. Okay. So, this is called the interpolation theorem. So, basically Nyquist sampling theorem and interpolation theorem together, they tell us that those samples, whenever you follow the criteria of Nyquist sampling, those samples are good enough to represent the signal. Okay. If you just pass it through those samples, if you just pass it through a low pass filter, you probably get your signal back. So, this is a very important result, and this also gives us some possibility of again multiplexing signals. So, that is something let us try to see what happens exactly. So, basically suppose the multiplexing was one of the important thing that was required for our transmission. So, we have said that suppose I have multiple signals, okay, and I want to simultaneously transmit that over a same media. So, let us say AR is the media, or if I have a wired media. So, everybody wish to actually simultaneously communicate through that same media. Okay. So, this is something we have done in amplitude modulation or even frequency modulation, so or general modulation theorem. So, what we were doing, we were actually in the same media, we were modulating with a different frequency of a carrier. So, what was happening in frequency domain, they were, suppose this is f corresponding to f1, this is f1f, okay, this is f2, or let us say g1f, g2f, and so on. So, this is at fc, this is at fc dash. So, we put them in different frequencies so that they coexist in different frequency band, and whenever we have to demodulate, we first employ a band pass filter. We have already seen that band pass filter is probably the first part of demodulation. So, we employ a band pass filter which is exactly matching with the desired signal. So, basically the desired signal will be at some frequency. If I already have understanding, means I know already that frequency. So, I will be putting my band pass filter centered around that, so that I can just filter out the desired signal and I can reject all the other signals. Okay. This serves two purposes. We have already seen that one is that it actually means take the desired signal, and also it rejects some of the noise which are present in the entire band. So, this is something we have done, and this particular technique was named as FDM, frequency division multiplexing. Okay. So, we were trying to do frequency division multiplexing over there, so that we can reuse the channel for means actually putting simultaneous transmission. Okay. So, this is something we have already discussed, we have done that through modulation. Now, by this sampling theorem, we have another opportunity. So, what is happening in sampling theorem? We suppose I have a signal, let us say that is again G1t. Okay. I put few samples to represent it. Now, if you just see it in time domain, these samples we have already proven through interpolation theorem that they are the sole representative of the entire signal. So, I do not need all the description of this signal for the entire duration of time. I can just take those few samples, that means discrete time description of the signal is good enough for me to represent the whole signal. Okay. If the signal is band limited, as Nyquist has already pointed out. So, if this is something which is happening, then I know that these samples are good enough to represent the signal. So, basically what this is doing, the sampling theorem is doing, it is freeing up some of the time which are not being utilized now for transmission of the signal. So, whenever we transmit the signal now after doing this sampling, we will be only transmitting those samples. So, only few instances of the entire timeline I will be transmitting those samples. Rest of the time my transmitter as well as my receiver will be idle. So, I can actually employ these things to multiplex other signals. Okay. So, that is my purpose now. What I want to do, suppose I have another signal G2T which is having a different shape. So, I also can sample. So, this was the sampling instance. So, these two signals simultaneously exist. So, time has unique definition. And what I do, because I know that these particular parts are free in time domain, and my sampling does not say exactly where from I start sampling. It can be anywhere, but only the regular interval should be maintained. So, if these two have equivalent bandwidth, okay, so that means this also is having B, maybe the shape is little bit different. So, minus B to plus B, and this is probably another voice signal. Suppose let us say this is voice signal. So, this is 3.4 kilohertz. I have another voice signal where the shape is little bit different, but it is still from minus B to plus B. If that is happening, then the sampling rate will be same, equivalent for both these signals. But what I can do, I can actually start sampling it little bit offsetted. So, let us say that is delta offset. So, then because the sampling rate is same, so it should be second sample also should be delta offsetted, and so on for every other samples. Now, what I can do, I can actually superimpose these things or add these two signal and transmit in the channel. So, how that will look like? So, there will be one sample from here, next sample will be from here, then one sample from here, next sample will be from here. So, if you just keep doing that, one sample from here and next sample from here. If we start joining the corresponding sample tip, you will get your original message signal back, but these samples will coexist in the channel. Now, what I have to do is, if I do this at the other end, I need to know exactly, the timing is very important. Earlier what was happening, when I was doing frequency division multiplexing, the frequency was important. The frequency information should be known, that which center, which carrier frequency I have modulated, I have to put my band pass filter accordingly. Here the multiplexing is being done in time domain. So, that is why it is called TDM, time division multiplexing, and the time information is very important. So, I need to precisely know where my first signal samples start. If I know that, I will only take this sample and then skip all the samples which are intermediate, which are due to multiplexing other signals actually. So, I skip this signal and I can pick this one just after that TS duration, that sampling means duration or intersampling duration. So, I can pick this signal as long as I am properly time synchronized, then I will pick this one. So, I will be picking my signals and then I reconstruct, that means I just pass it through a low pass filter, I reconstruct the whole signal and I get back my original signal. Okay. So, this is something which is possible. So, this has been made possible because of sampling theorem. So, you have seen there was probably in communication or analog communication, I should say, there are two fundamental theorems. One is called the modulation theorem, which actually if you multiply with a carrier, it translates the signal to a different frequency which is centered around that carrier, and if you sample it properly, knowing the bandwidth and then following Nyquist criteria, then you are actually freeing up some of the time between samples and where you can multiplex other signals. So, these are potentially two multiplexing schemes that has been employed in communication. You will see later on that mostly your means AM modulated signal, FM modulated signal goes through this. pulse modulated signals are, because it is already with a pulse, so it goes towards the TDM multiplexing scheme. So, it can still be done with FDM, and sometimes a mix of TDM and FDM is being employed. So, these are the things which can be done, but pulse modulated signal, they are closer to time division multiplexing, and that is why TDM is employed for multiplexing in pulse modulated signal. Okay. So, this is something which we have understood. Now, let us try to see another very fundamental thing in communication or in this kind of pulse modulated signal. So, what is happening? I have a signal, I sample it, right. Let us say these are Ts and my sampling frequency is 1 by Ts, okay, which satisfy the Nyquist criteria. So, that means Fs must be greater than or equal to 2b. Okay. So, this is something which is being satisfied. So, the minimum I can take to make it, let us say, because if I take bigger one, my samples will be closer because the sampling frequency increases. So, Ts will be decreasing because it is inverse of that. So, samples will be closer, less time I will get between samples. So, the best I can do is if Fs is just 2b, and I am sure that the highest frequency, whenever the bandwidth I define, highest frequency does not have any corresponding power component. Okay. So, that is something which is required, because otherwise there will be again aliasing. So, if the highest frequency does not have any significant power component, or it does not have any impulse or any kind of carrier. So, if I just sample it at 2b, then what will happen? This will be 1 by 2b. Okay. So, that Ts becomes, because Fs becomes 2b and this becomes Ts becomes 1 by 2b. Okay. So, this is something I already know. Now, let us try to see how much of information I am transferring, okay, with this. So, basically whenever I am transferring, how much information I am transferring? See how many samples I am transferring. Each of the sample actually carries information. Okay. So, if the frequency is, the time is 1 by 2b, frequency is 2b. So, basically 2b samples I am transferring per second, okay, and that occupies how much bandwidth? Whenever I am transferring it, of course, because of sampling it will go over here and all those things, but these things are not required for me. When I will be at the demodulator side, I will be putting a filter over here. Okay. So, basically my signal is confined over this. Okay. So, B, what does that means? So, basically this 2B samples I can now transmit with B bandwidth, because that is this 2B samples I am transferring, those are the information. So, 2B information per second I can transmit with B bandwidth, okay, or B Hertz bandwidth if it is represented in F domain, not in omega domain. Okay. So, with B Hertz 2B information I can transmit. So, per Hertz how much information I can transmit? Basically 2 information per second. So, this is a very fundamental result of, means later on you will see for digital communication this is probably the most fundamental result, that every Hertz, if you do sampling, every Hertz possibly carries 2 information, whatever that information is, per second. Okay. So, every Hertz is capable of carrying 2 information per second. This directly comes from the Nyquist sampling theorem. Okay. If you do sampling little bit, if you do oversampling, probably this will be little lesser, but this is the best you can do. Every Hertz at most can transmit 2 Hertz per second. Okay. So, this is a very important and fundamental restriction we should say whenever we employ sampling, and then each samples are information for us. Okay. So, later on you will see that when we from pulse amplitude modulation to pulse coded modulation, the PCM we go, this actually theorize the amount of bandwidth that is required for a PCM transmission. So, that is something we will see later on, but that is for now. For the time being, we should be happy about this result. So, basically in this particular class we have discussed 3 fundamental results side by side. One is the modulation technique, which is the multiplication with the carrier frequency, and there is a translation which helps us in FDM, frequency division multiplexing. The next one is the sampling theorem, which helps us in, this is actually sampling and freeing up some of the time. So, any signal does not have to be represented all the time, it just needs few samples, few discrete time representation of the signal. So, that is how we get time division multiplexing, or we have the opportunity to do time division multiplexing. And then we have also understood whenever we do this sampling and each sample becomes information for us. So, every hertz is capable of transmitting 2 information per second. Okay. So, that is the relationship between bandwidth and the information transfer rate. Okay. So, this relationship we will keep on talking about later on, and whenever you will be doing digital communication, probably this is the most important and fundamental postulate that you will be requiring. Okay. So, with this background, what we will do, we will start now exploring some of the more generic practical sampling that can be happening, because this impulse sampling is something which is impractical, because each impulse will have infinite energy, we have already proven that. So, that is not possible, we cannot really generate infinite power. So, we need to see if we employ some practical, which are the restriction of the circuits, if we employ those kind of sampling, what happens. Okay. So, that will be our next discussion. Thank you.